Okay, so this is an update of the slide deck that I presented last year, and boy, do we have a lot of news. And as we go through this slide deck, I will spotlight what's new. Um, when we did this webinar last year, we already had a kernel module. It was already in production with several of our customers. It already had many of the features that you're going to hear about today. But since that time, we have completed a lot of our roadmap for kernel module development, and it's a much more full-featured offering now. And as I said, you'll hear about that as I go through this. So just to zoom out for a moment, um, the kernel module it's based on our main product, the libwolfSSL library, which consists of two components. wolfCrypt is the cryptographic core. It has all the cryptographic algorithms, ASN processing, the base 16, base 64 conversion code, all the low-level algorithmic type functionality is in the wolfCrypt layer. And then we have a TLS, DTLS layer that sits on top of that. And we're going to be focused on the wolfCrypt layer. That's what our primary deliverable is in kernel space right now, is the crypto layer. We do actually build the entire library, including TLS and DTLS, inside the kernel, but it's not the TLS DTLS functionality is not currently a focus of our testing and deliverables. It's a roadmap item to provide deeper support for that. So the focus today is certainly on the FIPS 140-3 functionality in the kernel module. Now, all of our algorithms are built and tested in kernel mode. That includes non-FIPS algorithms like Cha-Cha-20 and future FIPS algorithms like ML-DSA. Actually, ML-DSA may now have been promoted to full FIPS status, but we follow emerging standards, and we make certain that old and new future algorithms are all already working correctly in kernel mode. But the focus for our customers, of course, is FIPS 140-3 compliance, and that is also the focus of our testing program. On x86, you'll get full performance just like you do with our user space library. We use the same code, the same assembly code, the same accelerations, the same architecture, the same source code in kernel mode and in user mode. So all of your experiences in every application that you've targeted in user space for libwolfSSL will also work. The same code patterns will work when you're targeting our kernel module. And we're fully compatible with kernels that have been configured and compiled with the native in-tree FIPS settings enabled. So I'll just go through some of the headline use cases for kernel cryptography that are currently supported by libwolfssl.ko, the kernel module build of libwolfSSL. So the most obvious one is, of course, disk encryption. Disk encryption needs to be done in the kernel. If you can do it in user space, and when you do, your performance drops from 4 to 6 gigabytes per second per core down to like 100 megabytes or 200 megabytes per second per core. So that's no good. You need to do your disk encryption in the kernel if you have any performance requirements, any efficiency requirements, and certainly if you're on a constrained endpoint where your clock rate is low, you need to run it in the kernel in order to avoid overhead. And we fully support that. And we support it with AES-NI and AVX accelerations. And it's completely no-code turnkey. When you load our module correctly configured, it will automatically replace the native non-FIPS implementation of AES-XTS with our implementation, and you are immediately up and running. And every encrypted file system that you mount after that point will use our implementation rather than the native implementation. Another obvious use case for kernel cryptography with similar dynamics around performance is anything to do with VPNs. So I didn't put it in this slide deck, but it's not just VPNs like OpenVPN or StrongSwan or other IPsec based VPN solutions that benefit from this, but it's also TLS offload, which is sort of VPN adjacent. If you load our module, then use TLS offload for the ASGCM encryption and decryption, you'll be using our FIPS code. So you're immediately FIPS compliant on the kernel side for the offload. And that's because we register our ASGCM implementations with the kernel with the highest priority. And that automatically causes the kernel to select our implementation to favor our implementation over all of the other implementations available in the kernel. And that is true for any application that you run. This is fully transparent. It's no code. There's no additional configuration that you have to do. It's just automatic that once our module is loaded, our cryptography, the FIPS certified cryptography, will be used for all cryptographic operations in the kernel. And you might say we buried the lead here. We now have our own VPN offering, which is a fork of WireGuard. We load as a second Linux kernel module that directly calls into our cryptographic kernel module, and it implements the WireGuard protocol, but with FIPS algorithm substitution. So we call it WolfGuard. WireGuard is a specific set of algorithms. It uses SHA-20 poly 1305 as the main symmetric AEAD cipher, for example. Ours is called WolfGuard, and it's the same architecture, it's the same usage, the same model in all respects as WireGuard. It just uses FIPS certified algorithms and implementations under the hood. And I can't stress enough that it works exactly like regular WireGuard. You can actually substitute the WolfGuard artifacts for WireGuard directly, and most scripting around WireGuard will continue to function because you can configure it so that the keys all look the same, even though under the hood now it's the P256R1 FIPS NIST certified ECC curve instead of curve 25519. But in practice, they look the same. And we do have crypto agility, including quantum resistant algorithms, including using ML-KEM under the hood. So that we will probably be delivering before the end of the year, the ability to use quantum resistant cryptography in WolfGuard. And that is a turnkey quantum resistant VPN implementation. And in our experience, the performance that you'll see, it's WireGuard and kernel network linked list limited, but you'll see north of 2 gigabits per second per core on WolfGuard with the quantum resistant algorithms in place. And that's what you see currently using ASGCM, and the P256R1 curve is north of 2 gigabits per second per core. So it's pretty good performance, and it works. The WolfGuard works exactly like WireGuard. And we do make use of the hardware intrinsics for accelerating the SHA operations and the AES operations under the hood also in WolfGuard. And I guess probably the single biggest thing to spotlight here is, since we last did this presentation, is that whereas a year ago we were only replacing AES-XTS in the kernel, now we replace 45 algorithms, including all AES modes, all the SHA and SHA-HMAC variants, including SHA-2 and SHA-3 and Shake. We replace the native DRBG, RSA Diffie-Hellman, elliptic curve Diffie-Hellman, elliptic curve digital signature algorithm. Those all get replaced by the FIPS certified cryptography with highest priority. And one of the trickiest things to replace turns out to be kernel entropy. It's not actually possible to replace kernel entropy without patching the kernel. So what we've done in order to square that circle is now we bundle a set of kernel patches that implement callback mechanisms. And on our module side, we use those newly added callbacks in order to register implementations of all of the randomness functions. And when you load our module with all the registrations enabled into a kernel that has been patched, and we support all the way back to kernel 5.10 for patching and all the way through to Linux Next, like 6.19 and everything in between. When you load the module into it, it registers itself and it replaces all randomness, all entropy generation in the kernel with FIPS certified entropy and FIPS certified DRBG functionality. And that includes even like utility integer generation that's used by network stacks and other sampling algorithms under the hood. So it's a comprehensive 100% replacement of all random byte generation inside the kernel with FIPS certified DRBG and a FIPS pending certified entropy source under the hood. So that's really cool. It was tricky to get it working, but we have it working, and it's now available to try out under GPL and to use under GPL or commercial license. All of this is dual licensed, so you can do whatever you need to do with it. So this slide is not updated since last year because it hasn't changed. Our performance in kernel mode is still roughly identical to our performance in user space. On most algorithms, we have state-of-the-art performance. We do have VAS acceleration of AES operations under development. And I don't have a timeline for that yet, but it is on the roadmap. And that will bring us to parity with the very latest Linux kernels. It's not much of an advantage, but it's a meaningful advantage, especially on AES XTS workloads. And I mentioned quantum resistant before. There's more quantum resistant cryptography to come, including registration of our quantum, like ML-KEM, ML-DSA, registrations of these algorithms with the kernel internal API backplane. That's another roadmap item. You can already use these quantum resistant algorithms, ML-KEM, ML-DSA, LMS, and XMSS. Those are already fully available and accelerated as native calls into our cryptography library or our cryptography module. The only thing that we haven't implemented yet is registration to make them available through the backplane by algorithms or modules that consume the LKC API backplane implementations. So the testing program for all of this, as you might imagine, is fairly extensive. We have a couple dozen kernel versions that we test on. We also have kernels from just about all of our kernel module customers that we run in every nightly testing workout in order to make certain that everything is still working exactly as expected with the kernel, with the customer's kernel as configured by that customer. So that once you're using us as your cryptography provider, we guarantee in perpetuity that if it ever worked for you, it will continue to work for you by keeping these kernels around. We don't sunset kernels. We actually have an old kernel 3.16 sitting in our stable of kernels that we continue to test on. Not because we have any customers that are using 3.x kernels, but just because that's how we know that we don't have any regressions and that nothing is gonna catch us by surprise. As anybody that's done development in kernel space knows, surprise is the enemy. Surprise is going to happen, and you need to be prepared to resolve it very, very quickly and not take on any technical debt along the way. So that's one of the reasons that we use the latest release candidate GCC. So our nightly testing includes using GCC 16 for the module builds. So we know if a future compiler is going to disrupt the behavior of the module. And we also test a wide variety of kernel configurations, obviously including the kernel sanitizer and the leak detector and fortify source and various other combinations of and FIPS on, FIPS off, etc. And I'm actually when we're done with the slide deck, I'm actually going to show what this QEMU system workout looks like in real time. It's kind of it's kind of fun to watch. So the Linux kernel is constantly changing. It's probably the most dynamic application development environment that exists. Um, Basically, every major release of Linux, of the Linux kernel, breaks something, changes something that requires that we tweak our glue logic in order to accommodate it. So we test, like I said, all the way back to 3.16. We also test on Linux Next. So this gives us really important coverage. Every night, an hour before our nightly library test workout begins, we pull the latest Linux Next from all the relevant Git repositories, and we build that new kernel, and that gives us early warning on breaking changes that will merge in the future to mainline. So that means we actually develop and typically merge glue logic fixes before the breaking changes even merge to mainline and become a release candidate. And that gives us a particularly strong expectation that our customers will have an assiduously smooth experience consuming our product. And we test on every LTS kernel version, starting with 4.4 through 6.12, and every one of them in between, and many more besides, plus all the customer kernels. And in our experience, you have to do this. The only way you can know that a non-trivial kernel application builds and runs correctly is to, on the target environment, is to test it in that target environment and to make certain that you have implemented self-test functionality in your test harness and in your application, unit tests, etc., that cover all the code that you need to make correct. So we don't leave anything to chance, and we test everything in multiple ways. This is an example of degrees of freedom in the target kernels. So we build with all of this stuff turned on and turned off, not exhaustively, but in a representative subset of the combinatorial universe of combinations. So these are the main ways that we are currently testing all of the kernel module builds. So of course we run our own mainline self-test routine, wolfCrypt test, that exercises all of our cryptographic implementations, all of our coding converters, the randomness and the big num, the big int, arbitrary multi-precision integer backend. All of that stuff is tested comprehensively by wolfCrypt test. We also test our benchmark routine. One of the things that we've added in over the last year is to these in particular, the test and benchmark sub applications, is calls to yielding routines so that they will no longer hog the CPU pathologically. And I mean, it's with the benchmark, it's not terribly important to do that because benchmark is obviously not a production functionality, but it was easy to do and correct to do, so we did it. Another thing that we do in our exercises for each of the targets is we actually simulate full dm-crypt file system operations. We create a file system, we under LUKS, under an encrypted file system, and then we save that file system and we use SHA-256 to get a fingerprint of it. And then we recreate that file system using, or access that file system using the other cryptographic implementation, and we make certain that it is bitwise identical. So we are creating it under in-tree cryptography and then reading it using wolfCrypt cryptography, and then we try it the other direction, and we make certain that it's always bitwise identical. So rather than just trusting that our that all of the unit testing on ASXTS, both the entry unit testing in the crypto manager and our own unit testing is giving us the ground truth, we actually exercise it as an encrypted file system to remove all doubt. Another thing that we've added in the last year is using libkc API to test from user space using third-party test vectors. This script was actually created years ago for FIPS 140-2. So what we do is we run this application with the FIPS 140-2 test vectors from user space and make certain. Obviously, we disable triple des and SHA-1 because those are not part of FIPS 140-3. But all of the FIPS 140-2 algorithms that are continued in FIPS 140-3, we test them through libkc API. That happens not to include the PK algorithms because the PK algorithms like RSA and Diffie-Hellman and ECDH, those are not actually available over KC API. It's or AFL. It's a historical accident, but it is what it is. And then, of course, we post-process the kernel logs in order to search for any of the problem patterns. We systematically put certain strings into our own self-generated error messages and warning messages, and we search for those in the test process. So here's a little bit on how we develop the kernel glue logic in order to make our kernel module work. So at the outset, when we started this effort about half a decade ago, the goal was simple. It was to make certain that existing processes for configuring and building libwolfSSL would carry over to the kernel module. And we did achieve that. And you switch from building a user library to building a kernel module. It can be as simple as just saying enable Linux KM. Now, usually that won't be enough because you need to tell it where your kernel tree is that you want to target. And you say that by saying -- with -linux -source equals, and then you just give the path. But in the simplest case, you literally can just say that, and you will get a kernel module built. There is only one source tree, and that source tree is used for heavyweight Linux user applications, for embedded applications, for the kernel module, for Yocto, for all targets. We only have one source tree, and that's where we do all of our development, and that simplifies things for us enormously to have a fully unified code base. Oh, and I should probably call this out. We do use native kbuild. We do not try to wrest control of the building process away from kbuild. We work with kbuild, and we work with kbuild from version 3.16 through version 6.19 inclusive, which can be a challenge, but it is worth the trouble because each kernel has its own idea that is configuration dependent, version dependent, and architecture dependent of the right way to build a module. And we don't want to second guess kbuild. So we use the native kbuild settings and the native kbuild toolchain in order to create the module. Now, one of the things you discover when you start developing non-trivial kernel modules is that many of your assumptions about how software engineering works don't apply any longer because the Linux kernel, it's not POSIX. We actually have to disable a lot of regular GCC warnings. Like we can't, when you build libwolfSSL, we have the compiler set to a very, very high standard of code cleanliness, a low threshold for warnings. So we have -w all, -w extra, and several other warnings turned on, and we make certain we stay clean on all of that on all of our supported targets, which is essentially all targets, because our portability is front and foremost for us. You can't do that with the kernel because, especially with older kernels, because the kernel was born in the early 1990s, before many of these warnings even existed. And it has been a long, arduous process cleaning up the Linux kernel to be clean on various warnings that modern code is already clean on. So the way we square this circle is that we disable those warnings only while including kernel headers, and then we re-enable the warnings. Some of the other differences are you only have typically a 16 kilobyte stack in kernel space. You can't make it bigger. and you can't if you overflow the stack, you are doomed. Um, and that is a very important objective for us in development, is to make certain that our runtime will never challenge that 16 kilobyte stack. Most of our, well, you'll see in a later slide what the stack high water mark is for many of our self-tests. But rule of thumb, we're typically not going to go past 4K. And often we're going to be significantly smaller than that. In the kernel, there's no red zone in the stack. You can't just use stack space a few bytes past your current stack pointer. That's something you often can do in user space. You can't do that in kernel space. So it's a small stack with no red zone. And there's also no C library. So there's something called the kernel library. The kernel library looks in many ways like the C library. It has similarly named string functions, for example. But obviously, it doesn't have any of the system calls, because a system call in kernel space is just a function, and you just call the function, and it's a whole different kettle of fish to use those functionalities from kernel space. And anything that you're doing in your library that's assuming that you have a regular C library won't port to kernel space, at least not trivially. And this is very easy for us to accommodate because we have targeted deeply embedded and bare metal environments with our library, particularly our crypto backend, for many years. That's been a mainline business for us. So porting our library to the kernel was actually unusually easy for us. But nonetheless, you can't assume. It's not the C library, and there are wrinkles when you port things. And you'll find that some functions you assume you'll have, you don't. There's no thread local storage, and that's fairly obvious in kernel space, because there are runtime contexts in kernel space that. So it's interesting. Everything is multi-threaded in the kernel, so you have all of the requirements of thread safety, but you don't always have a thread to associate it with, because when you're handling an interrupt, it interrupts some running thread. And now that running thread, so if you, for example, look at what your current PID is, an IRQ handler will actually, there will be a PID there, and it has nothing to do with the interrupt handler. So you have to make certain that any code you have that's paying attention to PIDs and such knows that it can't trust the PID if it's running in an IRQ handling context. And that's just more of the kernel is different sort of thing. The accelerations, all like ASNI, the SHA intrinsics, the AVX vectorization instructions, those are very awkward to use in kernel space, because the kernel doesn't actually save and implicitly save and restore those registers when you go back and forth between user space and kernel space. So when you go from when you swap from, or when the scheduler switches context from one user process to another user context, it is always going to protect those user processes from each other for all of the registers. But that is not true when a user process transitions into the kernel and then comes back to the same user process. It's an optimization. Most operating systems do it this way because most operating systems are only using integer instructions for a typical transition into kernel and then back to user space. We, however, do use, occasionally we even use floating point, but mostly this is about the vector instructions, and we use those extensively, of course, and we have to explicitly save them and then restore them before returning to user space. There are built-in mechanisms for doing this in the Linux kernel. They are architecture dependent. They are fairly awkward. They don't deal with recursion at all, for example. So we have to layer our own glue logic on top of that in order to properly deal with nested calls into our crypto layer to make certain that we use the ABI correctly. And I already mentioned earlier that the native kernel headers, it's not so true anymore, but older kernels would just, you get thousands and thousands of lines of warnings on printf formats not matching and signed unsigned comparisons and on and on and on. It was quite a mess. It's not so much a mess anymore, but we support kernels going all the way back to 3.x, as I said. So we don't have the luxury of pretending that that problem never existed. And I also mentioned that there is a treadmill of surprises. As the Linux kernel releases come out, we have to update our glue logic in order to accommodate the changes while retaining compatibility with all the old kernels. So in some ways, what we do is more complicated than what the upstream kernel community have to do, because we have to maintain compatibility with all kernels that our customers are interested in, simultaneously using the unified code base. So if you look at the Linux KM subdirectory of our product, you will see a lot of gates for a lot of different ranges of kernel versions, and it's because of that need to maintain compatibility with all of them. This is just a few examples over the years of things that have changed. The heap functions are particularly prone to change. 6.18 had a breaking change in it. That's actually still a release candidate. It's not released yet, but we actually merged. This is an example of our Linux Next testing program paying off for us. We merged the fixes for 6.18 before 6.18 existed, because Linux Next had the change in it, which told us that 6.18 would have a breaking change in it. So we actually merged the fixes for that into our master branch before it broke in the first place. And that's where we like to be. That's our offering to our customers, is that we will always be ahead of the curve. We will always have things working for you before you need them working. And you will be able to test it early and often for compatibility with release candidates, with future products. So I talked some about this earlier. The stack is very small in kernel space. We have a lot of testing. We have implemented stack high watermark measurement mechanisms in order to audit and test both as continuous integration tests before anything can merge in the first place to our master branch, and also in our nightly testing, we make certain that our stack usage is always under control. We of course have no recursive functions left, and we test for that. When in any stack constrained environment, recursive functions are a no-no. They may technically have an upper bound on their stack usage, but that's not a game that we're interested in playing. So we just don't allow any recursive functions in the crypto layer for the build settings that we use in the kernel module. And then, of course, there's just the basics of like keeping the stack frame small, keeping the high watermarks and the cumulative stacks small. And one of the obvious things is, so any multi-precision integer object is kept off the stack entirely. And the way we test for that is we build a library to support 16 kilobit RSA keys, which is big enough that it will blow past the maximum allowed stack frame of 2 kilobytes, and we make certain that that is warning free. So this shows you real world measurements of how much are so this is the full cumulative stack for unit tests. So it includes the test harness itself in these stack high watermarks. And you see that for like basic AES-256, it's a very, very small stack consumption, 1480 bytes, which is negligible compared to the 16 kilobyte typical available stack. Even on algorithms that tend to be hogs for stack space, we're quite small. And we have continuous surveillance for our stack high watermark on all of these algorithms. We never leave anything to chance in kernel mode. Our experience with leaving anything to chance in kernel mode is that it will come back to bite you every single time. So I talked earlier about using kbuild natively. Here's some more details on how we leverage kbuild, how we make certain that we are maximally portable by working with kbuild rather than trying to replace it or work against it. We just have a shim makefile that just hands off to a kbuild. I mean, that's the That's the main part of it. The shim header, the glue logic header in the Linux KM subdirectory, that has a rather large list of macro remappings and careful header inclusions and all of the sort of jujitsu that we have to do in order to make the rest of the library work as expected when building inside the kernel. We do use the ELF tools to do a pretty extensive post-processing to make certain that the library built as expected. And one of the reasons for that is that we have to containerize the entire wolfCrypt module in order to stabilize the FIPS hash. One of the awkward requirements of the FIPS standard is that the text and read-only data have to have a stable in-memory footprint that you actually run a digest across, and it has to match the digest that was computed offline. And we have to meet that criterion just as everybody else does, unless you get a variance, and we do not get a variance. We simply make it work. And one of the ways that we make it work, and I believe I have a slide that talks more about this later on, is that we build using PIE, position independent executable compiler settings. And we work around that. And that is actually able to solve the problem for us with a little bit of extra work. So we now have certificate 4718. It's valid through July 2029. And that's what our current fully certified Linux kernel module is based on, is the current valid full certificate 4718. We also have a module, we're on the module in process list for a follow-up submission that adds in ASXTS, several KDFs, streaming ASGCM, x86 acceleration. That submission is well along, and we never know when when NIST is actually going to approve a module. Nobody knows, but it is well along in the process. It's already in the module in process list. So this is the slide that I was promising, with some details on how we stabilize the in-memory footprint. So what we do is we rearrange the object using a linker script and obj copy, and then verified using readelf. All of this is just in the make files in the kbuild file. You can see it. It's in the GPL version. And what this does is it completely isolates all the wolfCrypt functionality of the larger module from everything else, which allows us to completely stabilize it and make it completely self-standing. It doesn't have any external references. And once you've eliminated the external references and you normalize the remaining relocations, now you have a perfectly stable in-memory footprint for both your text segment and your read-only data segment. And that allows us to meet the FIPS criterion for complete stability of the in-memory footprint of the implementation of all of the cryptography. So I talked about this earlier. There's no thread local storage. Our original FIPS implementation did use thread local storage in order to track certain things. We refactored that using native atomic operations for the kernel module. And now it's fairly straightforward. Another thing to point out is that FIPS 140-3 allows deferral of algorithm implementation verification until it's used. We don't use that. For the kernel module, we call this function at startup time. So when the kernel module successfully loads, it returns to user space with a guarantee that all of the algorithms have already been pre-verified and are available for use. So that's a completely unambiguous guarantee. At any point during runtime, you can actually trigger an additional FIPS integrity check that will once again run through all the algorithms and re-verify them. So I talked about this earlier. The vector registers are awkward to use, and we built glue logic. that makes it transparent for us inside the library and makes it recursion safe. So the future directions for the kernel module. So as I said at the outset, our focus has been on the cryptography side, but we do build, and we cleanly build, the TLS and DTLS layers, and we are aware of use cases for both TLS and DTLS in kernel mode. And something on our roadmap is to add in any missing pieces, to add in the test coverage in order to actually make this a turnkey product offering that you can terminate a self-standing TLS endpoint or DTLS endpoint inside the kernel. And just to be clear, it's not like with OpenSSL, for example, where you're offloading the symmetric cipher operations to the kernel. This is a fully self-contained TLS endpoint that is 100% kernel resident. It has no user mode aspect to it at all. That's the capability that's on our roadmap, and it might already work perfectly for a particular customer use case, but we can't make any guarantees yet. There are some algorithms that are missing x86 acceleration, and it's not a priority because these aren't FIPS algorithms. We do have the FIPS algorithms all accelerated in kernel mode, but it would still be nice to fill out our support for x86 accelerations. And so we have it here as a future direction. We're working on this right now. AArch64 assembly acceleration in kernel mode is a front burner development effort for us right now. It will be complete before the end of the year. So probably the release after next will include full AArch64 acceleration in kernel mode. And that's going to be very exciting. And of course, we already support the non-accelerated build in AArch64, and we will shortly support full FIPS, all of the FIPS tooling under AArch64 in kernel mode also. So before we get to questions, I have something that we didn't do in last year's presentation on this topic that I thought would be interesting to see is I'm going to actually show in real time how our test harness works. So it's going to run two tests here. The first one is our FIPS operational test, and you're just going to see thousands upon thousands of tests just streaming by at light speed, and then it's going to show all of the in-tree self-test using the crypto manager when it registers all of the algorithms. So let me get this going. Oh, and just academically, this test, the first test that's going to run with the operational test, it's actually targeting the Linux Next, and it's the Linux Next from last night. So this is running on the very latest code. And so you see, this is how we code it. We auto increment it. So this is basically release candidate for release candidate. It's a putative 6.19 kernel with October 22 as the timestamp on it. So this is the stuff that might be merging in the next kernel, or is expected to merge. This is just booted. No, that's our native self-test, and now we're running. These are the operational tests, and it's going to take a little while. But you just see it zipping by. It's just testing using it's comparing to various test vectors. It's looking for expected failure codes, expected success codes, and this is what this is what we prepare for our partner laboratories. Oh, and then finally, what you see here is rerunning our self-test to make certain, and then the green means everything worked as expected. And you see these are our diagnostics for successful stabilization of the in-memory footprint. The next test is, it's not the operational test, it's going to exercise the in-kernel, the native in-tree self-test algorithms. So it will start very similarly with our self-test routines running. There's the boot. So that's our self-test passing. And these here are the kernel in-tree registrations happening, which include all the self-tests. So when you see alg: self-tests, those are the kernel's native self-test using all of its compiled in native test vectors. This here is these are the libkc-API tests. This is so you see we're clocking about 4 gigabytes a second on the ASXTS benchmark. That's for a single core. And that's with a full-size key. That's a AS 512 XTS. And then we do it a second time, and a second time registering. Oh, so it's also testing deregistration and now re-registration, and all done. So that is the end of it. So it's time for questions.
Wonderful. Thank you, Daniel. Jumping straight into the questions. Is there Yocto support? If not, is it on the roadmap and current ETA? They couldn't find it on the GitHub.
Yocto support for the kernel, it's mainly a story of supporting kbuild. Obviously, Yocto has its own way of building packages, its own automation that is currently under development, and we do anticipate a turnkey Yocto solution for the wolfCrypt kernel module probably within the next couple months.
Wonderful. Before loading your kernel module, some hardware acceleration crypto algos, such as AES-XTS from Linux kernel, could be loaded and used. How do you ensure your kernel module is used and FIPS approved?
So the best way, yeah, that's exactly right. That any encrypted file systems that were mounted before our module was loaded will continue to use. They have open crypto handles that will continue to use the non-FIPS implementation. So the way you solve that problem is that you put our module into your init RAM-FS, and you load our module in your in your startup sequence before you mount your root file system. And then your root file system can be an encrypted file system and will use the FIPS AES-XTS implementation. And we have customers that are doing it this way.
Great. Okay, I'm not super technical, so I might mess up how you pronounce this, but about using libkcap test sh, are you mainly testing AES encryption / decryption? Libkcap does not support newer algos such as ML-KEM, LMS, etc.
In fact, it's a libkc API.
Oh, thank you.
And so I've scrolled up. You can see we're just testing the KDFs, the HMAC. We're testing what you can test. So we test all the AES modes, and we test all the SHA modes and HMAC modes. Let's scroll up here. It does rather go on, of course. These test harnesses are quite prolific. Here you see the SHA-256 and 512, and it's not actually testing SHA-3. libkc API is supplementary test coverage for us, and we're partly using it in order to make certain that AFAlg is working for us. We have comprehensive coverage with test vectors of all of the algorithms using the in-tree verification, the crypto manager, and using our own self-test, and using the FIPS self-test. So there's 3 ways that we verify all 100% of the cryptographic implementations inside the kernel module and inside kernel space. And then the libkc API testing is purely supplementary. We can't test any of the PK algs because the KC API doesn't natively implement PK availability through AFAlg anyway.
Perfect. Is this compatible with config preempt RT?
Yes. We have customers that run this in various virtualization contexts, and it works with all of them. And we have code in our glue logic that does the right thing with respect to preemption.
Wonderful. Is there RISC-V support, and is a Rust implementation on the roadmap?
RISC-V is on the roadmap. It might just work but we don't currently have testing for it. And as I said, with the kernel, if you're not testing it, assume you don't have it, but it's on the roadmap. As for Rust, we have a Rust layer for user space that allows you to use our crypto library from Rust applications. We have not looked at doing that in kernel space, but I will add it to our roadmap to look at it because that makes sense.
Great. You may have already answered this. What target architectures are currently supported?
So yeah, most of the presentation was focused on AMD 64. And you heard that our AArch64 effort is underway now. We have partial support on AArch64 without acceleration. We will shortly have full support with FIPS and acceleration. Um, we also have a customer that has used our port in MIPS. There's no acceleration. Obviously, there is no crypto acceleration in the MIPS target that we were working with there. But that gives you a sense of how portable it is, that it already works on AMD 64, AArch 64, and MIPS. That makes me think it probably wouldn't be hard to get it working under RISC-V or PowerPC, but you don't know until you know. So these portability things, portability efforts, they're driven by customer requirements. If you have a requirement, talk to us and we'll give you an ETA and we'll get it done.
Perfect. Our runtime is Yocto based and we are resource constrained. How big is the built module?
So it's so I did some checks on this yesterday in prep for today's webinar, and curiously, I was at 4.2 megabytes for the AMD 64 build with all the FIPS tooling, and I was also at 4.2 megabytes for the AArch 64 with all the FIPS tooling. So for FIPS 140-3 with all the trimmings, assume 4.2 megabytes. There's ways that we can make it a little smaller, but we can't make it a lot smaller than that. Obviously, once you start turning on like the TLS DTLS stack or any like debugging flags, it will get bigger in a hurt. So like -G3 is 25 megabytes.
And then I think this is adding to the earlier question, does Rust layer support all the functionalities, for example, wolfCrypt or TLS?
I'm not the expert on that, but it is growing rapidly, and we are converging on fairly comprehensive coverage in order to make it a reasonable experience for native Rust applications to use libwolfSSL as the underlying cryptographic implementation. And we are doing some internal refactors in order to constify arguments that we can in order to be able to label our functions as memory safe or memory safer opportunistically.
Wonderful. I think this is the last question. Can the TLS/DTLS stack be included in the module?
So yeah, I already answered that, and the answer is it can, but it's not tested. And if it is a priority for you, talk to us, and we'll make it a priority for us too.
Wonderful. Well, thank you, Daniel, for hosting an informative webinar. Thank you to everyone for joining. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at facts@wolfSSL.com. Thank you again, and we look forward to seeing you on October 29th for our webinar on how to secure AMD Xilinx platforms with wolfSSL. Thank you all.